In the last two videos, we looked at two different types of comparison tests, the direct comparison test and the limit comparison test. And we saw that we could sometimes use that to take a series that we want to learn something about to a series that we already have studied, so we already know that it converges or diverges. And we found that under certain circumstances, we can use one series to learn about the other. But what we didn't really address necessarily is how do we know what to compare to? How do you find the appropriate series to use as the baseline when you're trying to describe some other series? Well, it turns out that's a very difficult question to answer, and I cannot give you a foolproof way of determining the right comparison. But let me give you a couple of principles that you might use when you're trying to determine what to compare to. All right, so principles for choosing a comparison. And this is going to be when trying to tell if the sum of an converges or diverges. All right, so presumably we have some series, the sum of an, that we're trying to describe, and we're going to try to find some series bn that we can compare it to. And the first principle is make sure we know if the sum of bn converges or diverges. All right, it does not help to compare to another series if the new series is equally hard as the original one we're trying to deal with. We have to be able to determine whether bn converges, otherwise the comparison is completely useless. All right, secondly, consider the p-series as a candidate. So related to that first one type of series where we know the answer right off the bat is if you have the sum from n equals 1 to infinity of 1 over n to the p, we know that this converges if p is greater than 1, and it diverges if p is greater than 1, if p is less than or equal to 1. Okay, that's something that we proved in a previous video, and so that gives you a whole bunch of different candidates to try, and often that will be sufficient for quite a variety of different comparison problems. All right, so those are sort of two basic principles. Let's get a little more specific. The next principle is when you have a sum, in the numerator or denominator, you can often disregard all of the terms except the biggest one. And by biggest, I mean the fastest growing. Okay, so if you have something that has like n squared plus n, when n is large, the n squared is more likely to be the one that matters, and so you may throw away the n and just focus on comparing to the series without that term. All right, and then our last principle is when all else fails, make a guess if you think it converges. Look for a bn that is greater than or equal to an that also converges. Okay, so you may find the thing you have to compare to has nothing to do with the original problem other than the terms are bigger. And similarly, if you think the sum of an diverges, then what we're going to want to look for is something smaller that's also divergent. So look for bn less than or equal to an that diverges. All right, so we want a sum bn that diverges so that the sum of an must also diverge as a result. So that's basically making an educated guess, what we think happens, and then using that to guide our choices. All right, so that's all very theoretical. Let's actually try some examples and see what we can do with that. All right, so the first one I'd like to look at is the sum of 1 over 2 to the n plus n. Okay? And in this case, we're going to use that principle about the fastest growing term to help us here, because we have a sum in the denominator. And so we have two things that are both growing as n grows, 2 to the n and n. And of the two, 2 to the n is going to grow much, much faster. And so if this is an, let's compare to bn, which would just be the same series without the term that's smaller, without the n, because we think that's probably not going to be nearly as big as 2 to the n. And you can easily check if you plug in a large number, 2 to the 10 is much, much larger than 10. 2 to the 100 is way, way larger than 100, and so on. So 2 to the n grows significantly faster. Okay, so that seems like a reasonable starting point. Let's try to compare. First of all, let's start with something simple. How do 2 to the n and 2 to the n plus n compare? So forgetting about the fractions for a moment, let's just think about the denominators. And I think it's pretty clear that the one on the right is bigger. And if we take a reciprocal, or divide by 2 to the n times 2 to the n plus n on both sides, same thing, we'll end up with 1 over 2 to the n plus n is less than or equal to 1 over 2 to the n. All right? And what do we know about this series, 1 over 2 to the n? Well, that is a geometric series with ratio r equals 1/2, and so therefore it is convergent, since that is less than 1. And therefore, the sum on the other side I'll actually write down my entire series. Well, whatever this is must be smaller than something convergent. Of course, the terms are always positive here. We know that as well. And if you're smaller than something small, we can conclude that you are small. So this must converge as well. Okay? So again, the principle we used there is we disregarded the n. We threw that away when choosing our comparison because we thought that the 2 to the n would matter much more in the long run. All right, you could also use the limit comparison test here. It would require applying L'Hopital's rule, but you would eventually get to the same conclusion. All right, let's do another example. Let's look at the sum from n equals 1 to infinity of n squared over n to the 5/2 plus square root of n. Okay, now this one looks a little bit messy, but I think we can still make this work. First off, let's apply the same method that we applied in the last one. Let's look at this sum in the denominator. Of the two terms, which one is going to be the larger one? Well, the one with a higher power is going to be larger, and so this is going to be bigger. The other one is going to be smaller. And so that suggests that maybe this should behave like n squared over n to the 5/2, which you could simplify the powers of that. That would just be like, well, there's 2 and then 5/2 in the bottom, so that would just be n to the 2 minus 5/2, or n to the negative 1/2, which is 1 over root n. Those are all equivalent ways of writing the same thing. And so that suggests that the 1 over root n would be the appropriate thing to compare to. Now, if you think back to our principles, one of the principles we said is think about the p-series. The p-series is often a good choice for comparison, and we've stumbled on a special case of the p-series. This is just p equals 1/2, and if you recall, as long as p is less than or equal to 1, we know that the sum of 1 over n to the p diverges. And so this is a divergent series. Okay? So the thing that we want to compare to is divergent. Now, have we shown that the original series, well, that's an, converges or diverges? No, not yet. We haven't done that. We've got a conjecture, though, about what we could compare to help us answer that question. And the answer is 1 over root n. And so that may hint that this diverges, but we're not done yet. So now let's compare. In this case, a direct comparison seems like it's going to be a little messy. We could probably make it work. But let's try a limit comparison. Let's look at the limit as n goes to infinity of an over bn, which would be the limit as n goes to infinity of n squared over n to the 5/2 plus root n over 1 over root n. Okay, we could simplify that just a little bit by multiplying by root n on top and bottom. And so that will be root n times n squared would just give me n to the 5/2. And then I'll have n to the 5/2 plus root n underneath. And notice this denominator just becomes 1. And so now I've gotten rid of the fraction over a fraction. And it's starting to look good here. This looks like an indeterminate form, though. It's infinity over infinity. And so we can therefore, we could try L'Hopital's rule. I don't think that's going to help us a whole lot here. A better approach would be, again, to multiply by 1 over the fastest growing term. And we will get limit as n goes to infinity of 1 over 1 plus root n over n to the 5/2 is going to be 1 over n squared if you simplify the exponents. And that term goes to 0. And we'll be left with just 1. And so because our limit was 1, that means the sum of an and the sum of bn do the same thing. Right? Because our L, the limit that we found, was between 0 and infinity. That's what the limit comparison test suggests to us. We already know that the sum of bn diverges because it was a p-series. And so the sum of an diverges as well. Okay? All right, so there's two comparisons. We'll do one last example here. This one's going to be a little bit trickier. Let's look at the sum from n equals 2 to infinity of 1 over ln of n. Okay? Now, thinking back to our principles, that does not look like a p-series, right? There is only one term, right? There's no fastest growing term in the denominator or numerator that we can focus on and ignore the other stuff. There's only one term in the top and the bottom. So we obviously want to choose something to compare to that we know, where we know what it behaves like, but it's not at all obvious here. And so let's just make a conjecture. When we're thinking about series, and we want to know if they converge, we know by the nth term test that, first of all, the only way they could converge is if the terms go to 0. And even if they do go to 0, we've already seen some examples where the series can still diverge. And so ultimately, the way to make things go to 0 is to have the denominator, have the terms themselves go to 0 really, really fast, right? The terms need to get small very quickly. Now, if you think about this function, the log of n grows as n goes to infinity, so the denominator is getting bigger, but logarithms don't grow very quickly, right? So the log of 1 is 0, the log of 100, well, that's somewhere in the ballpark of, well, it's less than 10, and the log of 1,000 is still pretty small, and so you'll find that logs are very slowly growing functions. They go off to infinity, so the nth term test would say, well, an does go to 0, so that's inconclusive. But the fact that it grows slowly, that the denominator grows slowly, which means the terms go to 0 slowly, suggests that maybe this is going to be divergent. Because ultimately, again, we want terms to go to 0 quickly to get convergence. All right, and so let's think of another divergent series that we might compare to. And the first one that comes to mind that we've often referenced in some of our examples is the sum of 1 over n. Right? We know that this diverges. Whether we start at 2 or 1, it's going to diverge, and that's the harmonic series. And we've actually made that argument a couple of different ways. We made the argument by noticing that if you group the terms in a very particular way, you can see that, well, you're always going to get at least another half, and so it's going to keep going up by half over and over and over again. And then we also showed that this diverged by virtue of the integral test. So this one definitely diverges. And so maybe this would be a useful comparison here, since we think that 1 over ln of n might diverge as well. All right, so how do those two things compare? As always, I like to start without fractions, and so we'll just think about n and log n. And when n is large, it should be clear that n is going to be the bigger one. And therefore, 1 over log n is going to be bigger than 1 over n. So we just took a reciprocal there and flipped our inequality as a result. And so that must mean that the sum of 1 over ln n is greater than the sum of 1 over n. And, well, if this diverges, and the one on the left is bigger than something divergent, it must diverge by comparison. And this is a direct comparison. Okay? And if you don't like the direct comparison test, we could just as easily come to the same conclusion by looking at the limit as n goes to infinity of an over bn. In this case, we'd have 1 over log n over 1 over n, which is the limit as n goes to infinity of n over log n. And that's infinity over infinity, so applying L'Hopital's rule, we'll take a derivative of the top, and that would just be 1. And derivative of the bottom would be 1 over n. And if you have 1 over n, well, that wants to go to 0, which means this limit must be infinity. And if the limit is infinity, what we can conclude is that the one on top is the larger one, right? If the ratio goes to infinity, the numerator must be larger. And so an is much bigger than bn. Since the sum of bn diverges, the sum of an must diverge. All right, so that's two different ways of thinking about that one. Both a direct comparison and a limit comparison would work. And in that case, there wasn't an easy way to just simplify the expression and ignore some terms. But by making an educated guess based on what we know about how fast functions grow, we were able to choose a good thing to compare to.